In the last video, we learned how to find a confidence interval for a population proportion using the formula substitution and then finding the result with the calculator. Then we interpreted that value as we are 95% confident that the true population proportion is somewhere between those two values. Then we used those two values to find the point estimate, either by averaging them, literally taking the average, adding them up and dividing by 2 to find the middle of 0.25, or using the formula and getting 0.25 that way. But either way, we knew that it was 0.25, and that is the center of our interval. So now we want to find the margin of error two ways. We're going to use the formula and the interval. I'm sorry, my computer ate my video, so I've already got this typed up. I apologize. So remember the error is right up here in green. It's that distance from that center point estimate out to the edge of your interval. So you can do this with the formula. It's not pretty, but you can do it. So it's z alpha over 2 square root of p hat times 1 minus p hat over n. But the z we already know is 1.96 because this was a 95% confidence interval, and we already found the z-score for a 95% confidence interval was 1.96. We did it back on 2 pages ago, right here. The z for a 95% is right here, 1.96. I'll shade that just a little bit to make it different than the others. Okay, so now that we know that one, okay, then we would put in p hat and 1 minus p hat, etc. And we would type it all into a calculator and hope for the best. So I already did it again. Sorry, my computer ate my video. So 1.96 square root and then 0.25 parentheses 1 minus 0.25 close your parentheses divided by 120. And you get 0.077 and some change, which is where the 7.7% comes from. Now remember, way back at the beginning of this section, second page, right here, I said, think of your scoop as a pole, and then I had said, we estimate 25% of the beans are red, plus or minus 7.7 percentage points. Now you know where that came from. That error being 7.7%, right here, 7.7% comes from the formula. And you can see it right down here. That error that we're finding right there is from that formula. Now you could also use the interval to find it. So why do all that trouble with all that formula if you don't have to, I say. So remember that the error is equal to half the width of your interval. So the width is the pink zone from left to right. Well, half of that will be my error. So if I take 32.7% minus 17.3%, in other words, 0.327 take away 0.173, I subtract those and then I cut it in half. I should get the same thing. So 0.327, oh here, you want 1/2 times, and then parentheses 0.327 take away 0.173. See, 0.077. And of course, it's a little bit rounded. If you use more decimal places on those numbers, you'll get more decimal places for your margin of error, but it's good enough. And that's where this comes from, which is also 7.7% if you want to write it that way. So that's using half the width of the interval. Another way to find it would be to take the high value, which is 0.327, so, or error equals 0.327, take away the center, which is 0.25. That would also work, right? Because it's the distance between this pink edge over here and the center, which is the blue, which is 0.25. And if that works, there's another way as well. You could also take the blue edge center, which is 0.25, and take away 0.173. So let me write that. Or error equals 0.25, take away 0.173, which will be 0.077 as well. So that's 3 different ways you could find it. They're all perfectly valid. The one on the top is kind of the most true, but the bottom 2 will work as well as long as you find the 0.25 portion correctly. Oops, I got to turn off my track changes here. 1 second. There we go. So any of those 3 will work. Pick which one you like. The one that's the least prone to making a double mistake would be the top one, but the bottom 2 will work okay as well. All right, now let's talk about our confidence level. So if we increase our confidence level, leaving all other things alone, in other words, keep the scoop of 120, keep the 30 red beans, all of that stuff, what effect would increasing our confidence level have on our margin of error? So if you look at your formula, if you increase your confidence level, it's going to affect your z-score. It's not going to affect your p or your n because you're leaving the scoop, i.e. the n, alone, and the number of red beans, which is the p hat portion, alone. So if that's the case, if your error will get, if your error is this, increasing the confidence level will increase the z alpha over 2. To a larger number. And since this is in the numerator, it will cause the error overall to increase. Oop, I don't know what I did there. This will cause error to increase. And since error is, oh, that's all it wants to know. It just wants to know about the error. Keep in mind that would also cause the interval to increase. Right? Because the error is half the width of the interval. So if you increase your confidence level, you're increasing your error, your z. And if you increase your z, then you're increasing your error. And if your error increases, then so does your interval. It's kind of a logical argument. All right. Now that's kind of the formula way for why this works. Let me just kind of use a little bit of logic here with you. If you want to increase the chances, the confidence, the surety that you caught the big fish, right? You caught that parameter. You know that, well, you don't know, but you're really sure that that parameter is in this particular zone. So let me just say you're really confident that P is in your interval. Then you need to fish with a bigger net, i.e. you need to use a bigger interval, right? You're saying, look, leave everything else alone. I want to be more sure I caught the fish. Well, then use a bigger net, right? If you use a bigger net, you will be more sure you caught the fish, right? You'll be more sure you know where P is. Now, it doesn't mean you're 100% sure because we're never 100% sure, right? But it means that we're more likely to have caught the fish in our net if we go with a bigger net, if we go with a bigger interval. So that's kind of the logic for why this works. And then the formula says, look, if you want to increase your confidence level, then your z is going to get bigger. If your z gets bigger, because z is in the numerator, it's technically z over 1, if you like, right? Nobody ever writes it like that, but that's what it is. Since z is in the numerator like that, then that means that it makes the overall error larger, right? If this gets bigger, then this gets bigger. In other words, your confidence level and your error are directly correlated. And I actually just put that in right there. The error, E, error and the confidence level have a direct relationship, meaning if one gets bigger, the other gets bigger. Bigger, bigger, right? One gets bigger, so does the other. Okay. That's what we're describing here. Okay, now let's look here. It's asking us, suppose that a student in class claims that more than a third, see that right there? More than a third of the beans in the box were red. Does your interval support or contradict her claim? Okay, so let's see what her claim is. Her claim is that P is more than a third. So P is greater than 1/3. Okay, so now just on a side note, when I ask you a support or contradict question, don't say yes. It's not a yes or no question. It's either supports or contradicts. So this person is claiming it's more than a third. Let's look at our interval. Our interval is from right here, 0.17253 to 0.32747. So let me just remind you that. remember, the confidence interval was this, okay? All right, so they're claiming greater than a third, greater than, which would be greater than 0.33333 repeating. Remember, 0.333 with a repeating bar, it's got to have that repeating bar, is a third. Well, no, this whole interval is below a third. This is below 0.333. So the interval contradicts the claim because the entire interval is below 1/3. Let me just make a note. If the claim had been P equals, like the P is a third, that also would have contradicted. You know, a third of that box, right, is red. That would have been a contradiction as well. If the claim had been it's less than a third, then the interval would have supported them because the entire interval is below a third. So that actually makes sense. There we go. I just typed this up a little bit better. All right, so let me go back to what I was saying before. Sorry. If the claim had been P was equal to a third, then the interval contradicts that claim because a third is not in that interval. So they say it's greater than a third, no good. This interval is not greater than a third. They say it's equal to a third, no good. A third is not in this interval. What if they had said it's less than a third? Well, if they said it's less than a third, then the interval supports it because the entire interval is less than the third. Okay. Now, if they had said less than 0.3, contradict again, because you need the whole interval to be less than the value that they're claiming if you want to use that. Right? So it gets a little confusing, but we're setting you up here for some chapter 10 stuff, right? So this interval is contradicting the claim of more than a third. They were claiming more than a third. We contradict that because the interval is below a third, not more than a third. And again, this is setting you up for some stuff later on in chapters 10 and 11 when we're trying to support and contradict claims. So we don't know that this isn't true, by the way. It might be more than a third in that box. We just couldn't prove it, right? We didn't have the evidence to prove that more than a third of the box was red. It could very well be the case, but we don't know it. Our interval contradicted that claim because 1/3 was greater than the entire interval.